I'm at the Ethereum Foundation of the formal verification team that was recently started in the summer of last year. And I'm going to be talking to you about what we're doing and generally the state of formal verification of smart contracts as they are today. And I have a couple of different alternatives for the title of this talk where I want to emphasize slightly different things. So the first one, which also became the canonical title that went into the schedule, Smart Contracts as Inductive Systems, is emphasizing this particular way of thinking of smart contracts, which is particularly useful if you want to reason about invariance of smart contracts. That is, behaviors of the smart contracts that persist across the entire lifetime of the contract. Another, perhaps even more or equally galaxy brain sounding title has to do with the dual nature of specifications of smart contracts. And with this, as I will emphasize a couple of different times in this talk, I want to speak of specifications as playing two roles. As playing the role against which you check your implementation for implementation correctness, but also the fundamental building blocks against which you check for contract invariance or higher level design goals. So in that way, your specifications live on this middle ground where you can do a modular approach to formal verification up to them or up from them. And lastly, perhaps the most down-to-earth title is simply an update from the formal verification team, emphasizing the aspects of this talk that are more exploratory and that we haven't really fully figured out the appropriate way of doing everything yet, but we have some progress to share, and this is what I'm going to talk about today. So, another thing that I want to mention is that the slides for this talk will contain some links and some references that you may find interesting, and since they are hyperlinks, it's kind of hard to click them by just looking at this big screen. So instead, if you go to this URL, you will be teleported to this exact presentation and you can click them on your computer or just follow along as you see fit. So we begin with the question of what the appropriate way of thinking about smart contracts is. And of course, there are many ways in which we can answer this question that may be appropriate for different domains. I want to present two candidate views and then my own that will sort of sandwich in between these two high-level versus low-level views. So if we look at the coinage of the term, when Nick Szabo was writing about smart contracts in 1996, he says that a smart contract is a set of promises specified in digital form, including protocols within which the parties perform on these promises. And I think this definition is nice in some aspects. Specifically, it emphasizes the protocol of interaction, already keeping in mind that there will be different parties, perhaps debating or engaging over different things. It's quite close to a game theoretic view of a smart contract and the different moves in which players can make in that protocol. So those are the things that I like. Another thing that I enjoy about this write-up is that Nick Szabo already mentions some attack vectors of smart contracts. Whether it be naive vandalism, where you are not really gaining anything from destroying the smart contract, but just wrecking it and rendering it unusable for other people, or some form of incentive-compatible breaches, where you can personally gain from attacking it. But if we want to reason about specific smart contracts, I mean, this is an overly vague definition. And it's also somewhat interesting if we go into detail on this write-up that Szabo was doing, is that stake, or what these contracts are about, the sort of value inherent to them, seem to live beyond the contract. He mentions that intermediaries must be informed about the state or the past performance of these contracts. And so they don't really seem to live inherent to them the way that we think of smart contracts in the Ethereum ecosystem, carrying value in the contract itself. So it seems like proof of stake, for example, would fit in this definition. And that's not really an example that I would like to keep in my definition of smart contracts, as I'm going to use them for the context of this talk. He also mentions an important precursor of smart contracts being the humble vending machine, which I enjoy because vending machines are also used as a canonical example in many mathematical explorations of, let's say, linear logic or different kinds of state machines. They're being used to model many different kinds of systems, and they're also kind of nice. So here's an example of an important precursor of a smart contracts being a vending machine where you can buy wigs for your dogs. So on the other end of the spectrum, we have a way more precise definition of a smart contract, specifically of how we think of them in the Ethereum ecosystem from the yellow paper, not verbatim, but implied by everything that is being said there, where a smart contract is simply an address with non-empty EVM code. And it's nice that it's specific, like we can say lots of things about it. We can clearly point out what is a smart contract and what is not. We know that it can be stateful because we have storage in contracts, and we can say how they update over time through transactions and whatnot. But it's a little too specific in the sense that if you have two smart contracts with identical behavior and identical state, they would still be different smart contracts, just simply by living at different addresses. And so it's a little too granular for the purposes of this talk. And it also doesn't really say anything about attack vectors. So if you're a firm believer of this definition of a smart contract, you may be one of the people who say, for example, that the DAO hard fork attacker was not an attacker at all. It was simply utilizing the protocol as it was specified. So somewhere in the middle, specifically for the context of reasoning about contracts and their security properties, I like to think of smart contracts as stateful systems or inductive systems, meaning more specifically an initial state together with a finite list of stateful functions operating in a context of other stateful systems. Another way of saying this is that there are inductive systems with each external function method an inductive step in this inductive system. And I apologize somewhat confusingly for using two different definitions of functions on one slide in these two different paragraphs. What I want to emphasize is that in the first paragraph where I specify a finite list of stateful functions, these functions are mathematical functions, and so they have one output per input, and that they are stateful means that in order to specify the output of this function, we need to specify the entire state and the entire input variables that are relevant to its execution. It's essentially, to specify these functions, we would need to say what the pre-state and what the post-state is. And however we may reach the post-state, the algorithm by which we get there, what I call a function method in the second paragraph, is not really relevant to the definition of the smart contract itself. We could have isomorphic smart contracts that are implemented in different ways, but they behave similarly as inductive systems. I'll go more into detail on that later. But first, the picture to keep in mind when thinking of a smart contract as an inductive system is something like this. This is taken from Leo's presentation on the SMT checker at DevCon 5. And it sort of already shows you this inductive nature of a smart contract as being first defined by its constructor specifying the initial state. And then, depending on the methods of the smart contracts or the external functions available, you have these different ways of updating its state. But doing that update always puts you back to the interface, to the initial function selector of your smart contract, where every transaction begins. Every function call to your smart contract will begin in the interface. And so you really have this, well, let me show you this picture. You have a tree of that unfolds in front of you with all of the possible states of the smart contract. So beginning at the bottom, you have your constructor state, and then walking down a particular branch of this tree is a particular version of reality unfolding on the blockchain. But if you want to reason about the whole range of behavior or the whole possible states that your contract can be in, you really need to consider all possible nodes of this infinitely unfolding tree, which always have finite number of branches at each point. This is relevant because this is how we're later going to be proving things about this tree. Okay, so I'm going to say that in order to define a smart contract, we should define the initial state, and we should define these stateful function of which it consists. And to do that, we must declare for each function how they update the state, and if they have a return value, what that is. And so if you have done some stateful programming in Haskell, for example, this is very similar to how you would write some monadic function over the state monad. You can also define the design goals of a smart contract, and this is often, where the whole essence of your contract is being formulated. So instead of specifying what it is that your contract is, you can say what it should do. You can say that there are some fundamental properties that define your smart contracts. Perhaps that the sum of the balances is equal to the total supply. This is a very crucial property of any token contract. You can say that there's some fundamental accounting invariant that should be true of your smart contract. And these I will refer to as higher level properties or design goals of smart contracts. And they can also be verified once we have this definition. And finally, we have the implementation of a smart contract, which is writing an algorithm in Solidity or in any other smart contract language, even in EVM bytecode if you're leaning that way, by writing these algorithms that satisfy these specifications. And so most of the time, we really have to sort of infer the definition from the implementation, because most people, as they are writing smart contracts, are just providing an implementation. But then it becomes very hard to even say what its correctness criteria is. You sort of have to extrapolate some form of implicit correctness criteria that is only in the developer's head. But if we have these specifications, if we have all of the methods of the smart contract specified in terms of pre and post state, then we can do a very complete notion of formal verification. We can also do it in a very modular approach, because we can verify both the implementation and the design goals, the higher level properties, by considering how they relate to these specifications. So to go into a bit more depth on the first point, if we want to verify the implementation, so to verify that the code that we have written in Solidity or in the EVM matches the specifications if we have defined them, our strategy is most of the time going to be symbolic execution or model checking. And it can be done either on the source code level, so on the Solidity or Viper level. There's mainly only formal verification tools for Solidity right now when it comes to source code of smart contracts. You will be needing a formal semantics of the language in which you're writing your smart contracts. But then essentially what you're doing is demonstrating that the source code that you have written acts according to the specification. And so some of the tools that you can use to do this is the built-in SMT checker that is built into the Solidity compiler. There's another tool called Sol-C Verify, which has forked the Solidity compiler. And both of these work fairly well for some subset of things that you want to do. But they assume correctness in the compiler because they're just reasoning on the Solidity level. And so if you want to go deeper and you actually want to say things about how the bytecode behaves, you need to have a formal semantics of the EVM. And some tools that can help you do this is KVM, or the K-framework's definition of EVM, or Mithril. Mithril, somewhat interestingly, doesn't often deal with specifications at all. They just sort of try to infer some correctness criteria from a large list of commonly used smart contract patterns and common pitfalls associated with them. And there's a whole longer list of tools that I don't have time to go over right now. But if you're interested in getting a more comprehensive view, then we are maintaining a longer list of FV tools at this repository. So for the other type of formal verification, when you have these higher level properties or these design goals that you're interested in demonstrating that your contract behaves according to, your strategy for formally verifying that those actually hold is most of the time going to be induction, with some extra steps depending on the precise nature of your claim. And here again, we can split the concerns into two different categories, where the most straightforward one is when your correctness criteria is formulated in a contract invariance. And this is a predicate over state variables, so some formula that may contain some state variables that remains true for the lifetime of the contract. So regardless of which branch we walk down this tree, this formula will always hold. These can be further split into inductive and non-inductive invariants. I don't think that I'll have time to go into those details today, but I'll provide a reference at the end if you're interested in learning more about that. But just for some examples, I feel like there are not that many contracts that have formulated some sort of correctness criteria or design goal in this way. So here's a few of the ones that I know. For most, I would say, well-behaved token contracts, the sum of all of the balances should equal total supply. This is, again, maybe implicit from the ERC20 specification, which is not really a specification of anything more than the ABI. But we can sort of infer the intended meaning of what it's supposed to be. The other one, more esoteric, of course, comes from the infamously esoteric codebase of MakerDAO, is sometimes referred to as the fundamental equation of DAI, which, if you're unfamiliar with these obscure variable names, states that the sum of all of the DAI that exists in the system is simply the sum of the unbacked DAI plus the backed die. So the sin here is the unbacked die, so the system expenses as is minting new tokens for in the savings contract. But it also keeps, legitimately backed die in each CDP, and this is always multiplied by some accumulating variable that keeps track of the incoming interest rates on loans. The third one here is a somewhat simplified correctness criteria for Uniswap, which defines the product of the two balances of the two contracts involved, the two tokens involved in the Uniswap exchange as being a constant factor. So if you are asking for a particular amount of one token, then the price in the other token that you have to pay can be calculating according to this formula. But there are also more sophisticated correctness criteria that don't really fall into this category of invariance. And there's a whole range of further classifications that you can do, but for the purpose of this talk, I'm only going to call them non-invariance. But generally, these are criteria that are formulated in terms of maybe off-chain data or perhaps past call data that is not stored in the contract itself. And here we need to do some more, the quantification involved in order to make these statements require access to variables that are not directly accessible from within the contract. So let me just go over an example, and I think it might be a little clearer how these can look. So we're going to be looking into a little more depth of a recent formal verification project that was finished a couple of weeks ago, namely that of the Ethereum 2 deposit contract. This was a contract written in Viper, which was formally verified by runtime verification, which is also closely associated with the team that built the K framework in which the proofs were written. And this was a sort of end-to-end formal verification, meaning that they actually verified both the implementation and these higher-level design goals. And the higher-level design goal was not, could not be formulated as an invariant because it deals with call data of past transactions. So I'm not going to go into too much detail on how the deposit contract works, but generally the property that you want to prove of it, if you want to prove its correctness, is that when new deposits are put into the leaves of this Merkle tree that the deposit contract consists of, you don't store every leaf of the tree. Rather, you only store the minimal information necessary to recompute the root. Since you know that the right-hand part of the Merkle tree will always consist of 0 nodes, and you're updating it incrementally, you can recompute the root of the tree by only storing the red nodes in the picture. Okay, so the correctness criterion here is to show that this optimized version of the algorithm that doesn't store all of the leaves on-chain yields the same Merkle tree root as the one that does store all of the leaves on-chain. And so this was verified by RV, and this was done in 2 steps. They first built a high-level model of the system that simplified some of the implementation details and just tried to prove that the optimization employed is faithful to the naive implementation. And here they found a missing edge case, which was not really that important. I mean, it's mainly of academic concern, maybe, because it deals with a state that is very unlikely to ever be reached, but still interesting that you can find these things that your proofs really won't go through unless you have specified this edge case. They also found a couple of different implementation bugs, and now this has to do with the Viper compiler mostly, since the contract was written in Viper, all of which were addressed in subsequent releases of Viper. And I won't really go over the liveness subtlety, but it's there in the link if anybody is interested. But another reason why I'm bringing up this example is not just to talk about how you can do formal verifications, but also a little bit of an example of what the state of the art looks like. When it comes to specifying the behavior of smart contracts, there's quite a high level of detail and is not really that human readable by anybody who isn't intimately familiar with the K framework. And so I want to present an alternative to writing specs in this manner while maintaining the same level of formality. But first, let's talk about what we might want our specs to look like. I think that a specification should at least be a human-readable functional description with clear intended semantics of the smart contract in question. Clearness here being, somewhat vague, I admit, but for a more precise definition, you should say that maybe two implementers that don't know anything about each other's implementation should have two functionally equivalent implementations by just reading the specification. It should be implementation agnostic, I think, although it can use some common elements from different languages, as long as it doesn't commit too much to one route or the other. And when it comes to completeness, I think one sort of bar to keep in mind should be that it should be complete enough to cover the whole range of behavior that even if somebody wrote an implementation that was adversarial in the sense that they tried to cram in some backdoors, if you can prove that this implementation satisfies the specification, then there shouldn't be any backdoors like that. You should have a specification that is complete enough to admit anybody is submitting an implementation, and this being, as good as anything. So here comes ACT, which is the smart contract specification language that we're developing. And I'll give you a flavor of it in a minute, but let me just tell you what it is and what its goals are. It grew out of KLab, which was a tool that we developed to write K-specs in a slightly more human-readable language than the slide I just showed you. And it aims to be complete in that it should really admit adversarial implementations. You should be able to, once you have the specs for something, just add some implementation and check it against the spec. If it passes, then this implementation is correct. And this mainly deals with implementation, of course. So what ACT also aims to do is to support different proving backends that can either deal with the implementation or these high-level invariants or design goals. And so the first three targets of proving engines that we're dealing with will be KVM, SMT theories, and COC. And the sort of refinement that shows that the high-level model is faithful to the low-level specification should really come for free, in that the dual nature of specification ensures that both the implementation verification and the design goal verification is really dealing with the same fundamental specification of your smart contract. So here's an example. Here's a not a complete ERC20, but a minimal token that can at least transfer balances around. And something that I immediately like about this specification language is that it's roughly the same length as the implementation, a little bit longer. But it should be more informative in the sense that it may force you to think about cases that you wouldn't otherwise. Like the corner case where if you're sending somebody a token and this somebody turns out to be yourself, well, what should really happen? When you're writing the algorithm that implements this, since you're operating in an imperative environment, you are really performing these actions one after another. And so what happens is that you first give some balance away, and then you take that balance and give it to somebody. And now, since these somebodies are really the same person, nothing really happens. But if we look at the functional description of what this method does, then we need to specify these things as different cases, because if we are specifying the post state as a function of the input space, then it doesn't make sense if we assign two different expressions to the same storage variable. So every storage update that you specify needs to be relating to different locations. I'll go into more detail when it comes to the type of proof, the proofs that can be exported from this framework in a second. But I think that there are benefits outside of formal verification to having specifications like this too. And some of those are listed here. Most interestingly, perhaps, I think that this can be a clear target against which you can test and fuzz smart contracts. If you have a clear correctness criterion, then you can simply randomize your input and keep checking whether this correctness criterion continues to hold under all possible cases. Somewhat more speculatively, perhaps, is dealing with decentralized insurance, where you have some form of arbitrator which will reimburse you if a contract turns out to be broken. Well, now you have a very clear definition of what it means for a contract to be broken, because you've formulated its correctness criterion, and so then the reimbursement or the decision on whether to reimburse or not can be automated. So here's another example, which I hope is large enough to at least get a picture of what's going on. And this example is interesting for a couple of reasons, but first let me just give a taste of the different things that one would be able to export from a specification like this. You'd get the case specs, which deal with the implementation correctness. And since you have these conditions under which, well, they're translated to requires in the implementation. You have these conditions that must be satisfied in order for the function to execute fully and perform its state updates. You're really making two claims. You're making the claim that if these conditions are all met, then the storage will be updated in this way, and if they're not, nothing should happen. So this turns out to be two claims in terms of case specifications. One fail case, where you assert one of these conditions to be false, and one pass case, where you assert the condition to be true, and that the storage updates should be performed accordingly. And here's what the case specs look like. The second proving engine being SMT queries. Now this one is not dealing with the not dealing with the implementation correctness, but rather with this invariant that we have formulated right here. the invariant of this contract is that the relationship between these three storage variables is that the product of two of them equals the third. And so to prove this invariant, we can formulate the entire control flow of the contract as being given by two methods, f and g, and then a couple of rewrite rules, or in this case, horn clauses, that that model the control flow of our contract. We're saying that given any pre-state, we can either end up in a post-state which matches what happens when we apply the f function, or what happens when we apply the g function. And then the claim that we're trying to prove, well, here it's a negation of the claim that we're interested in, namely that there will never be a state that satisfies the there will never be a state that violates the invariance. If this is the case, we have an error. So doing a query like this would give you a counterexample. This is why it's negated. And then finally, the third backend is something that you would use if you were unable to prove the invariant with an SMT query, since there are some limitations to what you can do there. And when you're working with proofs in Coq, you need to do a lot of manual proving. So ACT would really just give you the definitions over which you need to make some manual proofs. So the final statement here is the proof that the invariant holds. And it requires some manual intervention. Here's a little bit of a technical point, so I'm just going to check how I'm doing on time. I'm not doing that well on time. So I guess to summarize what I want to say here, well, first of all, it's all summarized in this one README markdown file that I wrote. And it's exploring different ways of encoding the control flow of contracts and the types of proving methods that you might employ to prove invariance. Well, comparing two different encodings and showing that one works and one doesn't in this case. Okay, so let me just talk about some of the difficulties in developing the specification language, and then some of the future outlook, and then hopefully I'll have some time for questions. The most obvious difficulty is dealing with calls to unknown code, because this is really a fundamental source of unspecified behavior in your smart contract. You're saying if you have a method f that does some call in the middle of it, you're saying that you can clearly specify what happens up until this point where you do the call to some unknown code, but then clearly it's unspecified what happens, and then you return and you do some things. So this is not only hard to formulate in the specification language, but it's also hard to reason about what might happen. Another difficulty that I should mention is dealing with loops. Because to formulate the post state as a function of the pre-state when you have some looping recursive behavior can be quite involved, and you often need some manual intervention here too. Reentrancy also complicates this inductive view of smart contracts, because you can end up in states that are not isomorphic to your original state, and so to imply the inductive argument it becomes complicated. And so finally, I'd like to urge everybody who's writing smart contracts to be a little bit more diligent when it comes to writing specifications. What I've presented here is one approach to writing specifications, but even just having a natural language, so English specification, is a lot better than 99% of every project out there. And especially if you have some form of correctness criterion for your smart contract, then formulating this makes it easier for people to understand what your smart contract is about, but also to verify that it actually adheres to this behavior. So if you have some smart contract that you would like to experiment with specifying in this language, then I'd happily accept any examples, and maybe there might even be some formal verification proofs of your smart contracts if you do this. I think I'll end there. If you're interested in reading more about these things or looking at some of the examples that I gave in a bit more detail, here are first of all the slides and then some relevant repositories. Thank you very much.
Okay, so thank you, Martin. Great presentation about formal verification. Not great with timing, though. We can have time for one question only, if there is. No? I guess it's great then. So thank you.
Thank you.